Recrystallization is the purification technique used to purify solid organic products. When we do organic synthesis to prepare a compound of interest, the product that we obtain, we call it as a crude product because there might be side products or leftover reagent material left in it. Therefore, we need to purify our product of interest from the mixture to isolate it and get a pure product. And that is why we use this recrystallization technique. And this technique is based on the solubility differences of the solid organic compound in a solvent at cold versus hot temperatures. Let's take the solubility of benzoic acid in water at different temperatures as an example. Over here we see at 25 degrees or at room temperature, benzoic acid has a very low solubility in water, just 3.44 milligrams per milliliter. But you see that when we warm this solution to 40 degrees Celsius, the solubility increases somewhat. But if we continue to warm the solution to 75 degrees Celsius, now the solubility has increased by a lot. The reason the solubility increases with the temperature is when we heat the solution, we are supplying energy, and this energy is used to break the bonds that hold these solid molecules together in a crystal structure and forces these molecules to instead form interactions with the solvent molecules. So when we heat it, that energy causes the bonds between the crystal to break and bonds between the crystal molecules and the solvent molecules to form bonds. So that is what contributes to the increased solubility when we increase the temperature. And this is the concept that we use in the recrystallization technique. In this slide, we are looking at how the recrystallization works. Now let's assume these green crystals are the organic compound that we need to purify, and this red compound is the impurity that's trapped in the green solids. So these green crystals are insoluble at room temperature in this particular solvent. So you can see that this is a crude product. However, when we heat the solution to a higher temperature, the solubility of the green crystals increases in this particular solution. So when we heat it to a higher temperature, the green solids dissolve, and those impurities that were trapped in the crude solid are going to be released into the solution. Next, we allow the solution to slowly cool back to room temperature. Since the green crystals are not soluble in this particular solvent at room temperature, they're going to start to form the solid crystals again. And because this is a slow cooling, there is enough time for these green crystals to form strong bonds within each other where they have the best affinity and form a very structured crystal solid, leaving out the impurities in the solution. Now we can either filter or centrifuge. To separate these recrystallized solid crystals out of the solution. And now we will have the isolated pure product that we were interested in getting. When we do recrystallization, there's two possible processes that can happen. The one that we prefer is crystallization, which is a slow and selective process, and it generates pure crystals. Because the cooling down process is slow, a seed of crystal appears and it can selectively draw other crystals around it, and they can draw other crystals around it and form a very pure crystal lattice. Since this process is slow and selective, there is time for these crystal molecules to select their own kind out of the solution and form the best possible intermolecular interactions, leaving out the impurities in the solution. However, if precipitation happens, that is the case if you put this tube in, let's say, a beaker of ice, then this whole system is cooled down rapidly and the ice is going to absorb all the heat that was in this solution. And when the heat is absorbed really fast, it causes a rapid crystallization process, so these crystals don't have time to be selective and organized as in crystallization, but they're rapidly formed into a solid crystal lattice, and in that process the impurities get trapped within the crystal. And since we're trying to purify these crystals, precipitation would not allow us to achieve that goal, because the crystals obtained via precipitation is going to be impure. So the process we want to happen is crystallization, and that is why it's very important to allow the hot solution to cool down slowly. How would we choose an appropriate solvent for the recrystallization of our compound of interest? A good recrystallization solvent should display a low solubility for our compound of interest at low temperatures, but a high solubility for that same compound when the temperature is increased. So this blue line that has a steep and gradual increase for solubility of a particular compound in this solvent with the increase of the temperature would act as a good recrystallization solvent. B and C are examples of poor recrystallization solvents. If you look at B, the solution B has a lower solubility for our compound of interest at low temperatures. But even if we heat the solution to a high temperature, the solubility of the compound in this solution hasn't increased by a lot. So this behavior is not appropriate to obtain pure crystals by recrystallization. If we look at the curve C, it has a very high solubility for a compound of interest at even a low temperature, and it still has a very high solubility for the compound of interest when we heat it to a higher temperature. So there is no difference in solubility at low temperature versus high temperature. That's not what we want, right? We want a lower solubility for that compound in that solution at low temperatures or at room temperature, but we want a high solubility for that compound in that solvent when the temperature is increased. That is how we get the impurities to be released from the crude crystal lattice, and then we allow it to slowly cool down, and when it comes back to room temperature, we want our crystals to solidify again. So this curve A shows the behavior of a good recrystallization solvent. So when we have to choose a good recrystallization solvent for a particular product, we would look at their polar properties of the compound versus the solvent and make an educated guess what could be a good recrystallization solvent for that compound of interest. And if we have a few options, we would select them by trial by error. For today's experiment, you are given an impure sample of naphthalene and asked to use two potential recrystallization solvents, ethanol and hexane, and recrystallize this impure naphthalene sample to recrystallize pure naphthalene crystals, and then compare which solvent between ethanol and hexane served as the better recrystallization solvent. So the better recrystallization solvent should be able to have a better recovery of the pure crystals, and also the purity should be higher. So this impure naphthalene sample is actually a mixture of 90% of naphthalene mixed with 10% of biphenyl. So if we compare the polarity properties of naphthalene, biphenyl, ethanol, and hexane, we see that naphthalene is mainly nonpolar, biphenyl is mainly nonpolar, hexane is nonpolar, and ethanol is intermediate polar because it has this ethyl group and it also has this OH group. The OH group gives this molecule a polar property, while the ethyl group can serve as a nonpolar part of this molecule. So if we think about which solvent naphthalene would most easily interact with, we could say that naphthalene would most easily interact with hexane because they're both nonpolar and like dissolves like. For dissolving naphthalene in ethanol, we can see that it might be a little difficult because ethanol has a polar group and we might need to give a little push by supplying some heat to give more energy to force the naphthalene to interact with this ethanol solvent, right? So it looks like ethanol might show differential solubility for naphthalene at cooler versus higher temperatures. So from the get-go, just by looking at the molecular structures, it looks like ethanol is supposed to be the better recrystallization solvent. So how we do this is we are going to measure 0.1 grams of the impure naphthalene, add it to this piece of glass apparatus known as the Craig tube. We add 1 ml of ethanol, and we do the same with hexane. We measure 0.1 grams of impure naphthalene and add 1 ml of hexane. So at room temperature, if we look at them, naphthalene is not going to be soluble in ethanol. So these red particles are, we'll assume they are the impurity biphenyl that's trapped in the naphthalene crystals. And for the naphthalene in hexane, we would already see some of the crystals are soluble even at room temperature because naphthalene and hexane are both nonpolar. When we heat these solutions, when we supply energy, naphthalene is forced to interact with ethanol and become soluble, and these impurities will be released to the solution. And the same happens when we heat hexane. Then we allow these solutions to slowly cool down back to room temperature, and that selective crystallization happens here, leaving out the impurities in the solution. And the same should happen with hexane, only that naphthalene is more readily soluble in hexane even at room temperature. There might be a lower amount of crystallization occurring once they are already made to be solubilized. So based on the polar-nonpolar characteristics of these molecules, these are the observations that we hope to see during the experiment. Now on this slide, I have the data that was recorded from the experimental video. So for the recrystallization with ethanol, 0.1069 grams of impure naphthalene was weighed. And since we know that this impure naphthalene is a mixture of 90% naphthalene and 10% biphenyl, we can estimate the weight of naphthalene that was in that weight amount of impure naphthalene. So that times 90%, we can estimate there was this much naphthalene in the initial sample. Then after recrystallization, the crystals were transferred to an empty watch glass. So the weight of the watch glass by itself was taken, and the weight of the watch glass plus the crystals were taken, and their difference gives the weight of the purified crystals. And by dividing that by the estimated amount of naphthalene in the initial sample times 100, we can get the percent recovery of pure naphthalene when we use ethanol as the recrystallization solvent. So you can see it's not very high, but let's compare it with the data from the recrystallization with hexane. So this was the amount of impure naphthalene weighed for the trial with hexane, and 90% of that is this much. So that's the amount of naphthalene we estimate was in the initial sample. And after recrystallization, the crystals were transferred to watch glass, and the weight was taken for watch glass plus crystals and empty watch glass, and it looks like the crystals that were obtained were not sufficient to show a a measurable difference when we weigh the watch glass plus crystals versus just the watch glass. So you will see that you're unable to calculate the percent recovery for hexane, which means very small amount of crystals were formed. That means if we compare how ethanol did versus how hexane did in this recrystallization experiment, it looks like relatively ethanol did much better. And it kind of makes sense because ethanol is the one that is intermediate polar versus naphthalene, which is nonpolar, so they don't mix with each other readily. So naphthalene is not soluble in ethanol at room temperature, but when we supply heat, that forces them to interact, and that is when naphthalene dissolves in ethanol. But when you cool it back, since it's not soluble at room temperature, it will start to crystallize. But in hexane, naphthalene is nonpolar and hexane is also nonpolar, so they're both the same kind, like dissolves like kind. So we expect naphthalene to be more soluble in hexane even at room temperature, which would explain why it was hard to recover any measurable amount of crystals upon cooling down the hot hexane solution back to room temperature. Then another way to confirm the earliest slide was just looking at the recovery percentage, but that doesn't necessarily tell us anything about the exact purity of the crystals. Therefore, we can do a melting point test to find out the purity of the recrystallized crystals. So the melting point of pure naphthalene is 80.26 Celsius, and the melting point of the impurity biphenyl is 69.2 Celsius. So if our crystals are pure, we should obtain a melting point that is pretty much close to the melting point, or that we call it the theoretical melting point of naphthalene. But if our crystals still have some biphenyl mixed to it, the mixing of biphenyl is going to lower the melting point that we observe. So you can consider these numbers as the results obtained for the observed melting point for the crystals recrystallized either by using ethanol or by using hexane. And you can see the observed melting point for the crystals that were recrystallized by ethanol. The range of melting was between 80 to 81 degrees Celsius, which is very close to the theoretical melting point, and this range is also very narrow. That indicates the crystals that were obtained using ethanol as the recrystallization solvent were very pure crystals. Now let's look at the observed melting point for the crystals obtained by using hexane as the recrystallization solvent. You can see the melting point range is much lower than the theoretical melting point of pure naphthalene. So that indicates that the crystals that were obtained using hexane as the recrystallization solvent is not very pure. It has some amount of biphenyl still mixed with it. So by looking at this data, we can conclude that ethanol was the better recrystallization solvent. And in your discussion, you should explain why, what are the theoretical concepts that back this observation, like the differences between the polarity characteristics between ethanol versus naphthalene and hexane versus naphthalene, you should explain that and link it to this observation that you saw in the experiment.